When it comes to modelling multi-degree of freedom mechanisms like robots and cambots, there are some tricks and techniques that need to be understood to get the best out of MechDesigner. You can model functionally identical mechanisms in one of two ways in MechDesigner. In the first, you specify the output of your mechanism, and MechDesigner calculates the required inputs. In the second, you specify the inputs and MechDesigner calculates the output. The first way is useful for obtaining cam or motor profiles, the second is best for calculating forces. The most useful technique is to create two models and use the first to drive the second. In this way you can specify a path and analyze forces in one model. So let's look at an example. First I'm going to specify a path that we want a robot end effector to follow. So I'll edit the base part of a mechanism and add some geometry to define the path. Suppose we want to execute some kind of upside down J motion. So very quickly add the geometry, dimensions and constraints. I added a very useful type of spline called a blend curve to link to the two straight lines. This is useful because at its boundaries it matches position, gradient, curvature and the rate of change of curvature. This is analogous in motion to position, velocity and acceleration and jerk for a point moving along the curve at constant velocity. Okay, so this curve defines the geometry of the path. Now we need to define our motion along this path. To do this, we need to add a motion path function block. This will be driven by adding a motion and linear generator. It is important to make sure that the motion function block is set to linear, otherwise you may get some surprising results. Cycle the mechanism and you will see the point on the motion path move along the curve. Its distance along the path is defined by the motion. So if I increase the motion stroke, you can see it move further along the path. The kinematic values of the point are now functions of the motion and the geometry. This is important as you will be able to improve the acceleration of the point by modifying the curvature of the blend curve as well as changing the motion. Now we can start adding parts and joints of our robot. First an RRR joint, so 2 parts and 3 pin joints as shown. And notice that I changed the closure of the RRR dyad. So now we will build a slightly mad robot with 1 base pin joint and 1 base sliding joint. To do this I will add a slider and then a coupler and attach it to a point I put in earlier on the second link I added. Let's just check that this mad bot will cycle. So now we have a 2-axis robot which is driven by a path. This can't be used for calculating forces because it has a fictitious pin joint attaching the second link to the path. This will give the wrong answer because forces will act through this non-existent joint. So we must construct a geometrically identical robot but with different dyads. I will do this very quickly just to show what's involved. First I put in the identical geometry and parts. However, rather than driving the output with a path, I have used motion dimensions to define the positions of the robot input axes. If I add measurement function blocks to the lower model axes, I can use these to drive the second robot. The second robot does not have any fictitious joints and so will calculate forces correctly. The measurement dimension output is the wrong sign, so I can use a gear function block to change its sign. I have now added another measurement dimension to the lower robot to get the pin joint motion. This is connected to the top robot, but it looks like something is wrong though. When I added the trace curve I get a completely different profile, so I will check the geometry. Yes, the slider parts were different lengths. The trace curves look similar to the motion path. So I have geometrically similar robots, one driven by a motion path, the other driven by axis measurements from the first. In the next video I will show how to analyze the forces of this robot and select motors and gearboxes for the drive.